Hi, everyone. My name's Stuart Pearson, and I'm just wrapping up my PhD at the University of Technology in the Netherlands. And today, I'm really excited to share the latest work carried out by my colleagues and I at TU Delft in Deltaris. A lot of fun putting this together, and I hope you like it too. So this is the Dutch Waddenzee, which is located in the northern part of the Netherlands. And what I'd really like to point out here are these ebb-tidal deltas, which are essentially just large piles of sand located at the mouth of each tidal inlet. Form a really important part of the local sediment budget, and it's been recognized in the Netherlands that preserving these ebb-tidal deltas, partly by sand nourishments, might be a good strategy for mitigating sea level rise and coastal erosion. However, if we're going to do that, we need to understand how these ebb-tidal deltas will change at decadal time scales, and to do so, we're going to focus on Ameland Inlet up here. Now, before we go any further, I'm going to start with a little primer on ebb-tidal delta dynamics using an idealized version of Ameland Inlet. Here, the tide propagates towards the east, and we see a net flood tidal transport along the outer part of the delta, as well as along this marginal channel here, the updrift island. On the other hand, in the deepest part of the channel here, we see that the net tidal transport, and this results in the outbuilding of this shoal over here, and that's what gives the ebb-tidal delta its name. In the case of Ameland, we have dominant wave direction is from the northwest, and that drives some transport along the updrift island, as well as these shoals out here, and then down along the downdrift island. So together, these complex flow and transport patterns lead to a repetitive outbuilding and clockwise rotation of these channels and shoals. And as the old channels become less efficient and the shoals migrate downdrift, new channels take over and start this process anew, generating shoals of their own. So it's a bit like this guy's tail. Now, Blonde Ebb-Tidal Delta has a long and very rich history of bathymetric surveying, ranging from navigational charts in the late 1500s all the way through to annual surveys in more recent years. And this massive data set therefore makes Ameland a really good candidate for an investigation of modern ebb-tidal delta architecture. So we have all these old paper maps here that have been scanned in, and we see now, starting in the 1970s, really, we have these nice digitized data sets. And this high resolution really allows us to see how the ebb-tidal delta is evolving very clearly. And if you keep an eye, you can see this clockwise rotation and outbuilding motion that I described in the previous example. And here we are today. So our main problem is, how do we actually distill all this information and pick out what the relevant trends are? Well, today I'm going to show you two techniques that we've developed here. And one is with conformal mapping, and the other is to develop a stratigraphic model. This is based on a preprint that we've submitted recently to Geomorphology. And so if you're interested, you can check it out at the link below. Now, before we go any further, I just want to explain how we highlight the morphodynamic changes in the slides to come. If we start with the 2021 bathymetry, for example, and then we subtract the mean bathymetry averaged over all of the different surveys that we have, get what I've called the surface anomaly here. So essentially, the yellow areas correspond to areas that are anomalously high, mainly shoals, and the blue areas correspond to areas that are anomalously low. So these are mainly eroded areas or channels. Now, the first approach that we're looking at is conformal mapping. So what exactly is conformal mapping? Essentially, we're just taking something and transforming it into a more useful coordinate system. So what we'll do now is let's make a coordinate system that really aligns with those main axes of morphodynamic change: outbuilding, which we signify with rho, and the clockwise rotation, which we signify with theta. Now, we can then plot this ebb-tidal delta in the polar coordinate system, centered here in the inlet, and peel that orange to get this nice grid where clockwise rotation and seaward growth are more clearly visible. Now, let's consider the volume anomaly instead of the surface and the elevation. And this is the difference between a given surface elevation and the mean surface multiplied by the grid cell area. And this allows us to see where large volumes of sand are moving around. Blue generally indicates a channel and yellow a shoal. And again, we can unwrap this into the same polar coordinate system. How do we actually summarize all these changes over time, though? Well, if we sum each of the axes, then we get the total volume anomaly per row or column in a given year. And this allows us to basically collapse the dimensions of this big 4D time stack. And what we get from this then is each year forms a row in this total time stack, which then shows the clockwise motion I described earlier as a series of yellow ridges, which are shoals more or less, and blue troughs, which are these corresponding channels. Now, I've highlighted these rotational trends in red. And what can we conclude from this? Well, tidal deltas are not nearly as cyclical as I showed in that simple conceptual description earlier. They're repetitive patterns, sure, but each bypassing sequence tends to follow a different time scale. And this is important for coastal management because if we end up just waiting and assuming that we're going to get a sediment at some regular interval, then that could have dramatic consequences for coastal erosion and how we manage this erosion by nourishment. Now, something else cool that popped out of our analysis was that there's a clear trend in finding a reduction in variability as we move clockwise around the inlet. Now, this supports the notion of ebb-tidal deltas as a great big sediment sorting machine. So stay tuned because we're looking into this. Now it's time for our second approach, where we develop a stratigraphic model. So how do we actually develop this model from the bathymetry? Well, we have a series of idealized cross sections here. And if we compare the difference between two successive surveys, wherever it's higher, then we count that as deposition, and wherever it's lower, we count that as erosion. So if we go ahead to another year, we see that in this channel here, there's been some more deposition. This part gets eroded out, and there's more deposition up here. And these diagrams, dark blue corresponds to older sediment and older deposits, and yellow corresponds to newer deposits. So now let's apply this approach to Amelon, starting with the transect across the inlet. So again, keep in mind that dark blue is old and yellow is new. One of the main things that we see here is that this eroded island tip actually retreated about 3 meters over the past few decades. And what's left behind is this complex of shoals and channels that's extremely dynamic. There's lots of newer deposits here. There's also not exactly a lot of order. So there's a lot of very quickly shifting channels and things here. On the other hand, we have this channel fill in the main inlet channel. And this shows a much more regular pattern, gradually getting younger and younger as we move out and the channel migrates this way at this point. Now, if we take a look at this arc transect around the whole ebb-tidal delta, we can see some other cool stuff. So at this point here, we have, again, more channel fill in this abandoned channel. And then on the other side of the inlet, we have this very stable platform. And what we see is that these big yellow shoals that we see out here tend to migrate in a clockwise direction around this stable platform. And so this corroborates quite well what we see in the polar analysis that I showed you earlier, which isn't surprising because it's from the same data set. It just gives us two different approaches for slicing and dicing this kind of spatial temporal data set. And something cool is that when we compare this with existing geological models of ebb-tidal deltas and the ancient rock record, patterns that we see tend to correspond quite well. Now, how is this actually useful for coastal management? Well, it's nice because this can help inform our nourishment strategies because we can identify the more active or passive areas of the ebb-tidal delta so that if we're placing a nourishment, we want to go somewhere more dispersive or to just sort of be more preserved in the volume of the ebb-tidal delta. This approach gives us a better understanding of how the area is structured. And it's also useful for siting marine infrastructure. So if you're trying to run a cable or a pipeline or something through here, you can clearly identify which the more dynamic areas are versus the more stable parts of the delta. And it's also useful for marine salvage operations. For instance, we have this little triangle in here, and that corresponds to the location of a measurement frame that was buried during our last field campaign. There's a great big storm, and this whole big shoal just migrated right over top of it, and we haven't been able to get it back. It's buried underneath about 4 meters of sediment now. So, but based on the rate of migration that we observe, I suspect that possibly sometime in the next 5 years or so, it could get unearthed, unless, however, this channel starts to fill in, and in which case, then it could very well be decades before that is unearthed again. Now, where do we go from here? Well, we'd like to try this at other sites because I think the nature of this approach lends it well to maybe a more improved generalization of ebb-tidal delta dynamics. And also, we want to apply this to numerical model output because I recognize that we're extremely lucky at Ameland Inlet and that we have such a rich data set of these historical surveys, but that's not the case everywhere. However, if you have a morphodynamic model, you can basically construct your own multi-year bathymetric data set like we have here and apply the same kinds of approaches. So in the end, we have this conformal mapping and the stratigraphic modeling approach, and it just gives us new ways of looking at decadal scale morphodynamics and stratigraphy of these deltas, and just new ways of looking at old data, and it's pretty much applicable anywhere that you have enough data or this kind of model output. What do I want you to come home with? Just that this conformal mapping and stratigraphic model allow us to squeeze more value from these bathymetric data sets. Thanks for your time. If you have any feedback, our paper is still in review, so I'd love to hear from you.